we have with us Dr. Onur Mutlu. He has a broad range of research interests in computer architecture, systems, hardware security, and bioinformatics. He started at the computer architecture group at Microsoft Research, and he has had various product and research positions in leading industry enterprises. He's a recipient of numerous awards. He's a ACM fellow for contributions to computer architecture research, particularly in memory systems, and IEEE fellow for contributions to computer architecture research and practice, and is also an elected member of the Academy of Europe. And just recently, this week, he has also received the Outstanding Researcher Award from Intel. In a couple of talks earlier in the day, we were hearing about the challenges around some of the bottlenecks being data and how quickly data can actually be shifted. So one of the challenges that performance is limited by how applications end up using data. So this next talk is really going to shed a lot more light on what approaches and what we can do about that. It's on memory-centric computing. So looking forward to learning, Dr. Mutlu.
Thank you very much, Ashok, for the kind introduction. I'm going to share my slides right now. I assume you can hear me and see the slides well, right? Okay, great. Okay, I'll get started then. Thank you for inviting me for this talk. I'm going to talk about memory-centric computing. This is actually, in my opinion, a fascinating area, and I can talk very long about it, and I have a lot of slides, but we'll not go into the details of the slides, but I'll hopefully give you the high-level picture of where things are heading in memory-centric computing today. So hopefully, based on the discussion so far, it's clear that data is really key for performance and efficiency of many applications. And important workloads are all data intensive. They require rapid and efficient processing of large amounts of data. And we are doing increasingly sophisticated things on the data that we process. And on top of this, data is increasing as well. We can today generate more data than we can process in many domains. I'll give you an example of multiple domains here. These are some example workloads where data is increasing and we're doing sophisticated things on data. And as a result, data is a performance energy bottleneck. And if you look at the memory system, many properties of the memory system become a bottleneck. It's really a complicated set of properties: capacity, latency, bandwidth, energy, reliability, all interact to become an interesting bottleneck for these workloads. If you look at the mobile end, we're also running many workloads. In fact, we're exercising almost all of these workloads right now, I would argue. And again, the data is a performance energy bottleneck on the mobile end as well. And if you look at some, let's say, futuristic or interesting developments in genomics, for example, we see that data is becoming an even bigger bottleneck in those workloads because genome sequencing is critically important for many applications, of course. But our ability to sequence genomes has become much better over the course of last decades. The cost of sequencing a genome has reduced greatly compared to Moore's law, as you can see over here, which this symposium is titled about. But you can see that we can now sequence many genomes at low cost. The question is, what do we do with that sequencing data? And that becomes a problem. Basically, sequencing is not a problem today because we have good technology, but mapping of those sequences to something that we understand and making inference out of those sequencing data has been the bottleneck. As a result, our scientific discoveries and other things that we would like to do with genome analysis, like medical advancements, very quick, real-time interaction with the patient as well as the doctors, so that doctors can make very quick decisions based on genome data, is really bottlenecked by the data that's coming out of the sequencing machine and our analysis capability. And this becomes even more interesting with sequencing technologies that look like this. I'm not going to go into the details of this, but we do a lot of work in this genome sequencing area and its acceleration. But you can have devices as little as this today, and as that have relatively little cost, for $1,000, for example. Unfortunately, these devices are great at generating data, but they're terrible at analyzing data. So you need to move the data all over the world to actually do great analysis on this data. And it can take weeks to actually get the answer that you really want. And it comes at a cost, of course, energy cost as well as performance cost. So this is another example of how we can generate data, but we cannot really process the data efficiently today. And if you're interested in this area, we have written some articles on this topic. This is a primer article that talks about some basics, let's say. And we do work on FPGA-based near memory acceleration. I'm going to talk about this paper later on. And also more accelerators that are designed both for FPGAs as well as ASICs that do approximate string matching. So I find this a fascinating area. And we really need to tackle the data problems in many, many directions. And this is a paper that's upcoming in a couple of weeks in ASPLOS, where we actually do in storage processing of genome sequence analysis. We do very aggressive filtering of genomes without losing accuracy, so that we don't move the data from the storage into the computation unit or even memory. And I think the future is actually very exciting in this direction because the sequencing devices are going to get more capable. They're going to get cheaper and cheaper. They're going to get more efficient. But our data analysis also needs to keep up with this in terms of both performance and efficiency and cost. And unfortunately, in my opinion, today, we're not designing devices that are scalable, efficient, and low cost. And if you're interested in this area, we have a lot of talks and lectures in our architecture classes. I'd refer you to those because I'm not going to talk about genome analysis more. This was just an example application that I believe is really important that we can enable. And clearly today, for example, today with the COVID-19 outbreak, these genome sequencing engines have become even more important. They were always important in my opinion, but with something as urgent as COVID-19, they've become even more important. And these sequencing machines have been used all over the world to actually understand the COVID-19 genome and its variants, or RNA and its variants, basically. So this was an example showing that data actually overwhelms modern machines today. It overwhelms the storage and memory capability, communication capability, and in the end, computation capability as well. You may have a great computation engine, but because it's bottlenecked by data, it may be sitting idle. Data greatly impacts robustness, energy, performance, and cost. And if you look at a computing system, fundamentally, it consists of three key components: computation, communication, and storage and memory. And over decades, we've heavily optimized the computing units. So we're very processor-centric. And I would argue that we mostly ignored the rest of the system. Of course, ignored in relative terms, right? Clearly, if you look at a processor, a node today, we're very processor-centric. All data has to go through the processor to be processed. And these could be the cores, these could be the accelerators, these could be the cores in a GPU or in an FPGA. But basically, if you look at a node today, most of the system is dedicated to storing and moving data. Even though these are called computing engines and we're processor-centric, most of the processor itself consists of caches, interconnect, other caches, other interconnect, memory controllers, other interconnect. And if you go off chip, shared memory, other interconnect, and storage. And if you do the calculation, more than 90% of a single node is dedicated to storing and moving data. And even then, the system is still bottlenecked by memory. Maybe we're doing something wrong with the design of our systems then. So to give you some numbers, we've studied these workloads together with Google. These are Google's workloads, actually. And we published this paper where we showed that more than 60% of the entire system energy on a mobile system is spent on data movement, just for data movement across the memory hierarchy. We're going to get back to this. And this doesn't even include the data movement from the storage. And data movements from the storage can be even a bigger factor, as we will discuss later on in this talk. So my axiom going further in this talk will be that an intelligent architecture, if you want to design intelligent architecture, and I would argue that we would like to design intelligent architectures going into the future, as previous talks have mentioned. And also, we want these architectures to make decisions for us, critical decisions, life critical, safety critical decisions for us. They need to be intelligent and they need to handle data well. So the question becomes, of course, how do we handle data well? I think there are three major issues over here. We want to ensure data doesn't overwhelm the components we design, be intelligent algorithms that are frugal in terms of how they treat the data, be intelligent architectures that are also frugal, and we have whole system designs, algorithms, architectures, devices across the stack so that we can minimize the overwhelming of the components, so that the components are actually balanced with the data demand. Second, we would like to take advantage of vast amounts of data and metadata that's flowing through the system so that we can improve this architecture and system level decisions using online learning methods going into the future. So today, for example, the systems we design are mainly based on heuristics that are dictated by humans. So as a result, system actually makes human-driven decisions. They don't actually learn from the past behavior, just like humans do, for example. As humans, we have great learning capability, but as hardware or systems in general, they don't have learning capability. Can we actually incorporate learning capability to the fundamentals of the system such that you can make better and better decisions as the system becomes older and older, let's say. And third, I think we would like to understand, exploit properties of different data. Today, the systems we design actually are usually agnostic to different properties of data. Data has a lot of properties: security properties, privacy properties, approximability properties, error tolerance properties, performance properties, locality properties, compressibility properties. You can actually keep adding to these properties. Unfortunately, these properties sometimes are not very well known, sometimes are not discovered, and definitely they're usually not communicated to the underlying system or architecture. As a result, system and architecture doesn't know how to prioritize its policies, basically. If this data is very security critical, the system doesn't know that, so it cannot take a good action about it. So we really need to have an interface between the higher levels of the software stack and the lower levels of the system and the architecture, so that we can communicate the different properties of the data in a general manner, and we can take advantage of these properties underneath. So that brings me to the corollaries, which I kind of explained actually. Today's architectures are not good at dealing with data. They're mainly processor-centric as opposed to data-centric. Basically, everything has to go to the processor to be processed. Nothing else in the system is capable of processing on the data. And we're going to mainly focus on that one in this talk. Architectures today are not good at taking advantage of vast amounts of data and metadata. They're basically ignoring a lot of data. They make human-driven decisions as opposed to data-driven decisions. As an example, the cell phone I have in my pocket is 6 years old, and its memory controller has seen a lot of applications, it's made a lot of decisions, but it hasn't learned anything from its decisions, basically. It's seen a lot of environmental conditions. It's experienced me many times, but it didn't learn anything out of 6 years. I would argue that if it was a fundamentally intelligent engine that was data-driven, if it was actually learning from the data and changing its decisions based on, for example, different learning principles, reinforcement learning is one example, it can actually make much better decisions. And we actually, I'm not going to talk about this direction much in this talk because we don't have time, but I think this is actually very important for the data-centric systems as well. And we've been working on memory controllers and prefetchers and memory systems and storage systems that can make these decisions in a much better way using reinforcement learning, as opposed to humans dictating the policies. And I'm happy to talk about that separately. The third direction is architectures today do not know or exploit different properties of application data, as I mentioned. They're designed to treat all data as the same. As a result, they make component-aware decisions. For example, a memory controller, when it looks at the memory system, it says, oh, I have these banks available. I have these row buffers open, and these rows are open. So they make very structural, component-aware decisions, as opposed to higher-level data criticality-aware decisions. Oh, this data is more important than this other data. We don't take that into account today. I believe going forward, architectures need to be much more data-centric, data-driven, and data-aware, so that we can actually treat the data much better. In this talk, I'm going to focus mainly on the data-centric parts because we don't have a lot of time. But I have slides actually that cover data-driven and data-aware, and I'm happy to share the slides. So of course, this requires revisiting the entire stack, in my opinion. We need to look at algorithms all the way through devices and co-design them in some way. And we must take an expanded view of computer architecture, co-design algorithms to device, and specialize as much as possible within the design goals. Hopefully in this talk, I'm going to give you some examples where we can actually gain orders of magnitude performance in some cases, actually, where you do this design completely end-to-end. Okay, so let's jump in. Let's jump into the data-centric or memory-centric architectures. And if you think about this, even a data-centric architecture has multiple different properties. I would argue that you would like to process data where it resides. You need to respect data, meaning you need to have low latency and low energy access to data so that you can process the data quickly and energy efficiently. You need to have low-cost data storage and processing engines. And there are a lot of ideas over here, which I'm not going to get into. I'll briefly motivate. And you need to have intelligent data management. Intelligent control is handling many, many aspects of data and the system: robustness, security, cost, performance, etc. So we're going to talk mainly about the first part, processing data where it resides. I will also rename it as processing data where it makes sense. So today, data resides in many parts of the system. It can reside in tape. It can be gathered in sensors. It can reside in the storage system. It can go into the memory system. It can reside in caches. I would argue that we need to enable capability of processing data wherever it resides, because there are different trade-offs in different parts of the system. And if we can enable the capability of processing data wherever it resides, we can actually design a much more fundamentally efficient system. And this also includes a network, for example. But of course, this is not a new idea. This idea is actually quite old. As you can see, it's almost 60 years old. These are some of the early papers that are more clear in terms of what they define. And you can take a look at them. This is Harold Stone's famous paper from 1970, for example. I would argue that this is certainly interesting, and this idea has been explored for a while. But today, we're in a much more pressing position to actually consider in-memory computation and make it real. Why? We're being pushed in two directions. One is the bottom direction, technology layer, and the other is the top direction, systems, architectures, and algorithms. I'm going to cover these quickly, especially the first one more quickly. We have a big push from technology today, meaning underlying devices, especially DRAM, dynamic random access memory, which is the memory device that is dominant in all computing systems. It's not scaling very well. We're having a lot of reliability issues, a lot of energy issues, a lot of latency issues. Even bandwidth is becoming difficult to grow, basically. As a result, the industry is open to new memory architectures, and they're putting controllers close to DRAM. And these are some examples that people are looking at. For example, 3D stacking architecture, where you have logic layers tightly integrated with memory layers, and different ways of doing processing inside the memory. And more recently, more aggressive ways of doing processing inside memory by UpMem and Samsung, which we will talk about later on in this talk. So a lot of this is motivated by memory scaling issues, technology scaling issues. And these issues have actually been real for a while. DRAM has not been scaling very well for a while. And you can look at this talk that I delivered in an International Memory Workshop a number of years ago that kind of outlined the issues that we will see, in my opinion. And later, we did a lot of studies. This is a study from that we did with Facebook, where we basically showed that as the chip density increases, you get more errors in data centers. And this is because as the chip density increases, fundamentally, your memory cells become less reliable, as well as they become closer to each other. As a result, you get more noisy behavior inside your circuits. And this reflects itself as server failures in your data centers. And if you're interested in this, you can study this paper, and many other papers have been written on this topic afterwards, as well as before. We built a lot of infrastructure to actually study these memory scaling issues. These are FPGA-based infrastructures where we actually test many memory chips and understand the fundamental behavior of these memory chips. We open source it. If people are interested in doing studies on their own memory chips, they can actually use this. We actually have some newer versions that I will mention later in this talk. While we're doing that, together with Intel, we discovered that you can actually predictably induce memory errors in most DRAM memory chips, essentially bit flips. This should clearly not happen, but technology scaling has become so bad today that you can actually do this. And this is known as the row hammer problem today. Essentially, you have disturbance errors. Whenever you access one row, which means that you apply high voltage to the cells in the row, you can disturb the cells that are physically adjacent. So this happens when you do this, especially repeatedly. So whenever you access a row, you apply high voltage to the word line, and then you apply low voltage. And then if you keep doing this, apply high voltage, low voltage, high voltage, low voltage, high voltage, low voltage, meaning activate and precharge, activate and precharge, activate and precharge in DRAM. If you do it enough times before the cells get refreshed, it turns out physically adjacent bits in adjacent rows get flipped in vulnerable DRAM. And most DRAM is vulnerable today, actually. So we call this the hammer row, we call it the victim rows. And we showed that in more than 80% of the chips that you can buy from 3 major DRAM manufacturers, there are only 3 major DRAM manufacturers today, are vulnerable to this effect. And this is really a technology scaling problem because you could not do this in earlier chips. But in all chips that were manufactured between 2012 and 2013, we saw this happen. And we have actually more recent data in 2020 and 2021, actually, that's showing essentially the same thing. So this can actually be a security problem. This technology scaling issue can be a security problem because someone can take advantage of these bit flips to take over your system. They can definitely corrupt your data, no question about that. But they can actually use these bit flips to take over the system. I'm not going to go into the details of it. There's actually a very rich literature in security, starting from this Google Project Zero, which basically showed that they can exploit their DRAM row hammer bug or vulnerability to gain kernel privileges in using otherwise a user level program. So they can basically become root in your system by taking advantage of these bit flips. So more recently, people have demonstrated that these neural networks that may be used in safety critical applications are actually vulnerable to these bit flips as well. For example, a neural network that's reasonably accurate, more than 90% accuracy, can lose its accuracy to down to 10% if someone actually flips the bits in your memory or in the memory of the accelerator that's executing the neural network. And I would refer you to these papers. And I find that this is actually a bit scary because we want to rely on these neural networks for many, many decisions in our lives, especially safety critical decisions are most concerning in a self-driving car, for example. And if we can actually not guarantee the safety, reliability, and security of data that these neural networks rely on, you can get decisions that are actually much worse than what a human would do, much worse than anything would do. 10% accuracy is actually something that's not to be proud of, I would say. So I would say that these technology scaling issues are actually causing a lot of trouble. So if you look at this bridge, this is the Galloping Gertie. This bridge looks very important. It's important infrastructure. And if you get a bit flip in this bridge, which has happened in 1940, this is what happens. But today we have much more critical infrastructure. Computing is a much more critical infrastructure where we will rely our lives on. And unfortunately, if you have bit flips in our computing systems, we may not be able to trust our cars like Mr. Bean trusts his car over here. So this is an example of a technology scaling issue that I believe needs to be solved with intelligent controllers. And if you're interested in RoveHammer, you can clearly watch our lectures and read a lot of papers about it. And these are the works that have introduced RoveHammer, showing that memory scaling issues are actually real. And more recently, we were invited to write this retrospective paper that I would invite you to read if you are interested in the more broader perspective of RoveHammer from both software, hardware, and device levels. So why am I telling you all this? Basically, it's a technology scaling issue. It can be solved with intelligent controllers. If you put some intelligence into your controller, you can detect such issues. Today's controllers are not very intelligent. They cannot detect such issues. But I think going forward, we need to design controllers that can detect these technology scaling issues and that can make a memory much more reliable, safe, secure, and much more understanding of the issues that we have with data that's stored in memory. And this is an example of intelligent controller. I don't have time to talk about it, but this is one solution that we have developed that is reasonably competitive and scalable. And industry is writing papers about these technology scaling issues also. This is a paper from Samsung and Intel that was written in 2014 that basically shows that DRAM process scaling is not going well. So we need to really design intelligent controllers. And another example of technology scaling issues is DRAM scaling is not going well. So we're looking at other technologies like phase change memory, magnetic memory, RRAM. There are many other technologies, or different types of DRAM can also be considered more scalable DRAM technologies. And going forward, we need to have perhaps heterogeneous memories, hybrid memories, and this is already happening. These different memories have different characteristics that are green, meaning good, and different characteristics that are red, meaning bad. And maybe we should be designing intelligent controllers that can exercise the greens of each technology as much as possible while avoiding the reds of each technology as much as possible. This is an example of intelligent controllers and hybrid memory enabling better scaling. And this definitely requires intelligent controllers that understand the properties of the memories, as well as the properties of the data, so that they can map the data to the right memory, so that they can achieve the best of multiple technologies. And finally, there are many examples of intelligent memory controllers, but this is another intelligent controller that's very relatively recent that we developed, where we showed that you can identify uncorrectable errors in memory chips that already use error correcting codes if you have an intelligent controller that knows how to profile the errors. Okay, so I think the takeaway from this part of the talk is that if you have intelligent memory controllers, you can avoid many failures and enable better scaling of the memory system into the future. And that's the push from circuits and devices. We really need intelligent controllers. That's why we're getting pushed towards doing processing in memory today from the circuits and devices perspective. Now, let me give you the high-level perspective that squeezes us in the middle. We have a big pull from systems and applications as well. Meaning today, data access is a huge bottleneck. Applications are increasingly data hungry. Energy consumption is a key limiter in all systems that we have. And data movement energy dominates computation energy. So let's take a look at this in Synchrony. But before I go into it, I will mention something that's extremely important, in my opinion, for our world. Do we want a world that looks like this going into the future, sustainable, where future generations can thrive? Or do we want a world where future generations are actually threatened to live? I would argue that we want sustainability, no question, and we want energy efficiency, but we also don't want to give up high performance. We need to find a way of actually enabling all of this, because high performance is critical for solving critically important problems, including the climate problem that we have created, let's say. So for this, I think we need to examine the fundamentals of computing. Today, data access is a major performance energy bottleneck because we're moving data all around. Our current design principles, the processor-centric paradigm, causes great energy waste in our world. And it's going to increase basically as we scale up the computing infrastructure in all of the world. This causes great energy waste because we're moving data between the, let's say, where the data is generated or stored into the processing units. This causes great performance loss as well. I put this in parentheses because today we employ many software as well as hardware techniques, as well as system level techniques to overcome this performance loss. And we're still not good at it, I would argue. There's a huge performance loss because of movement of data. And we employ many techniques like multi-threading, heavy software, let's say redundancy, caching, prefetching, many levels of memory hierarchy, out-of-order execution, complicated processors, and they also cause great energy waste in the end, especially when they do not work. And there are many applications where these techniques do not work, or a good fraction of these techniques do not work. So today we're in a vicious cycle where we keep generating energy waste because we're moving data, and we keep generating energy waste because we made our systems a lot more complex to tolerate the performance loss that is caused by the data movement. So to get out of this vicious cycle, I think we need to really fix the problem at the fundamentals of it, which is processing of data today is performed far away from the data. That's why we're in this place to begin with. So we need to revisit how we actually look at the three key components of the system. We have heavily optimized computing system, computing unit. We are very processor centric. As a result, we cause great system cost, which reflects itself as energy inefficiency and sustainability problems. Yet we know that memory system is a big problem. So I'm going to give some data relatively quickly. And we've known this for a long time. This is a quote from Dick Seitz, who was the chief architect of alpha processors in 1990s. After they designed a flagship alpha processor, he wrote this one-page article in Microprocessor Report, which was titled, "It's the Memory Stupid." Basically, he said that we designed this processor that can finish 4 instructions in a given cycle, but this processor is finishing 1 instruction every 4.5 cycles in this important database workload. Why? Because it's waiting for data to come back from memory. And he finishes his article saying that I expect that over the coming decade, memory subsystem design will be the only important design issue for microprocessors. Okay, fast forward about 10 years. This is data from my own PhD thesis, which we did gather together with Intel. This is data from all of Intel's workloads that they used to design their processors, flagship processors with. And we found out essentially the same thing. Most of the time, the processor is waiting for data to come back from memory. Fast forward 10 years later, this is data from Google on a flagship Intel processor that they employ in their data centers. Essentially, in their important workloads, these are all of their data center workloads according to Google, and you can read the paper for more detail. It's a beautiful, beautiful paper. They basically show essentially the same thing. Most of the time, the processor is waiting for data to come back from memory. It's finishing useful instructions only 10 to 20% of the time. And this is the peril, I believe, this is the quantified peril of processor-centric design. We have a grossly imbalanced system. Processing is done only in one place. As a result, data moves a lot. This is low performance, complex, energy inefficient. And even though we have an overly complex and bloated processor and accelerators, we actually have this energy inefficiency and low performance and complexity in place. So this is the processor that we're kind of talking about, right? This is a kind of an abstract level of thinking. As I showed you earlier, even though the processor is processor-centric, most of the system is dedicated to storing and moving data. Memory system is still the bottleneck in this processor. Let me give you the energy perspective quickly. This is data that I borrowed from Bill Daly. These numbers are old, but the takeaways are still the same. So if you look at a complicated arithmetic operation, it consumes about 20 picojoules. Moore's law has helped us a lot by scaling the logic. The technology scaling, Dennard scaling also helped us a lot. And memory access is 800 times higher energy. So basically, if you actually use the more recent technology, let's say, and optimize things, and memory access still consumes about between 2 to 3 orders of magnitude the energy of a complex addition. This is the success of actual transistor scaling. Transistors logic has scaled really well over the course of 70 years, but interconnect did not scale well. As a result, memory system, which is dominated by essentially interconnect, has become the energy bottleneck. And if you're interested, you can read more papers on this. As a result, we have more than 60% of the total system energy in a system spent on data movement. I would argue that we do not want to move data. If we're really this performance and energy constrained by data movement, and also reliability and security constrained, as we have discussed earlier, we do not really want to move data. Basically, we need a paradigm shift to enable computation with a minimal data movement. We need to compute where it makes sense, as opposed to just the processor, basically where data resides. And we need to make computing architectures much more data-centric as opposed to processor-centric. So this clearly requires a rethinking of the entire system architecture. I'm going to focus on mainly the main memory in the rest of this talk, but I believe that the opportunities in the entire system architecture, including the system architecture that we build across the world. We really need to revisit how do we do computing in the tape, for example, in the storage and the interconnect, in the data centers versus edge devices. And we need to minimize the data movement. We need to actually be very frugal about it. I'm going to focus on memory because memory is a very interesting place. And if we enable it in memory, maybe we can enable it in other places more easily. So memory today, a lot of applications are actually designed to be in memory, meaning they fit memory. Databases, graph processing, media processing, neural networks, etc. we would like to design a system where the processor says, memory, can you execute this function for me? And the memory sends the function results back to the processor. So we would like to have memory actually as an accelerator, and going forward in equal footing with the processor. Perhaps memory is an independent agent that can actually execute an operating system also going into the future. So there are many questions, of course. How do we design the compute-capable memory and controllers? How do we design the processors and communication units? How do you design the software and hardware interface to enable this? How do you design the system software compilers and languages to make it exploitable, easy, high performance, and efficient? And how do you design the algorithms to take advantage of the underlying devices and also analyze the algorithms using theoretical foundations of computing so that we can actually make this better and make this, put this into a theoretical framework? So basically, this requires rethinking across the stack, algorithms to devices. And I will mention the theoretical foundations over here because I think this is important. If you analyze algorithms today, algorithmic complexity is all about counting operations. Big O notation, big theta notation, for example, you count operations, which means that it's mainly processor centric. It doesn't take into account the amount of data, at least in a direct way. So going forward, I think we need to develop theoretical foundations of computing that's very data centric if you want to enable a data centric or memory centric system, which I hope is well motivated by now. So I'm going to give you some examples of processing in memory in the rest of this talk, and hopefully give you some hope that this is actually happening little by little, and hopefully we will make it happen in a larger scale as well. But if you're interested in this in more detail, this paper, this overview paper that we have written at the end of the prior year, well, last year actually, during the last year, can give a lot of other ideas if you're interested. And these are some excerpts from that paper. But I would argue that we need to think differently from the past approaches. And processing in memory today needs to be a little bit more, let's say, based on different approaches that are fundamentally different from each other. And I will distinguish between two ways of doing processing in memory. One is processing using memory. The second is processing near memory. Let me talk about processing near memory, the second one, quickly right now. So today, processor is here, memory is here, they're far away from each other. The idea in processing in near memory is to get the processor closer and closer and closer to memory. At some point, processing is inside the memory. And you can use new technologies to actually make processing immersed in memory. So there's a distinct processor and distinct memory in this particular case. They're designed using different designs. And the programming is somewhat similar to today, basically. It's still a von Neumann processor, I would argue, that gets closer and closer to the memory. So processing near memory is more closer to what we do today, except processor gets closer. And as a result, the data movement bottleneck gets reduced and reduced. On the other hand, processing using memory is fundamentally different. The idea over here is that you have a memory device, it can store data, but you realize that it cannot only store data, it can also do computation. It has some fundamental operational principles based on its circuit level operation that you can take advantage of to actually do computation on the data as well. And I will show you this example. Now, this is something that people have not thought of as much, let's say, and I think we need to think more about it. How do you use a storage device and use its operational principles for computation? How do you tweak its operational principles to do better computation as well? So I'm going to start with this processing using memory. And I could do this with any technology, actually. SRAM, DRAM, phase change memory, magnetic memory, resistive RAM, hard disks, SSDs, flash memory. Enabling technologies are many. So the basic idea is to take advantage of the operational principles of memory to perform bulk data movement and computation in memory. You can exploit internal connectivity to move data. You can exploit analog computation capability as well. And I have a lot of examples, but I'm going to cover some of them over here. I'm going to start even simple, actually. I'm going to talk about data copy and initialization. Today, we actually do a lot of copying and initialization of data in our systems. For example, imagine initializing a 1 terabyte database. You write a lot of zeros or some value into memory to initialize a database. And Google recently showed that just 2 function calls, memmove and memcopy, occupy 5% of the execution cycles in their data centers. That's a lot for just 2 function calls, memmove and memcopy. So today, if you want to do the copying, you have to go through the processor. You have to copy a page, for example, from memory to the processor's caches, and then do the copy to a destination page, and then write back the destination page to memory. This is not very efficient. In future systems, I argue that we need to do the copy in memory, meaning that if you want to copy this 4 kilobyte page, which is small, into another 4 kilobyte page, you do it completely in memory without disturbing anything in the processor. And this is low latency, as I will show you. This is low bandwidth utilization on the most important resource, perhaps. no cache pollution, and no unwanted data mode. So there's a lot of benefits basically. And you can see that for a 4 kilobyte small copy, you can reduce its latency by more than 10x and reduce its energy by more than 70x. And that's the idea. I will not go into the operational details quickly, but the idea is actually very simple. If you want to do it in the DRAM, the fastest way of doing it is inside the DRAM subarray. The source page and the destination page are inside the DRAM subarray. The idea is to first activate the source page, which brings the data into the row buffer. And then you activate the destination page, which takes the data from the row buffer into the destination page. And using the charge sharing principles between the sense amplifiers and the DRAM cells, you can do this back-to-back activate reliably. Basically 2 consecutive activates, negligible hardware cost. With minimal modifications to your main memory, you can actually do this reliably. In fact, if you do not do any modification to your memory, recent work, including ours, has shown that you can basically mimic this 2 consecutive activates by violating the timing parameters in the memory controller, such that you fool the DRAM chip to actually do this 2 consecutive activates, and you can observe this behavior in many DRAM chips today. So you can do this almost completely reliably in many DRAM chips, even though the DRAM chips are actually not designed to support this operation today. So imagine what you can do if you actually design the chip to support this operation in a valid manner. And as I said, the performance and energy improvements are significant. Ignore the other bars over here. If you actually want to move data between other parts of the memory system, it takes a bit longer and a bit less efficient, but actually we have other solutions that I'm not going to talk about in this talk, but I will point you to another talk if you're interested. So that's the idea of row clone. With such a simple idea, thinking data-centric, you can get significant benefits. And recently we put out a real system row clone prototype where you can do this on a real system. You can take this FPGA-based infrastructure that's open source, and you can experiment with it. We're very open to feedback based on what you find out. And if you're more interested in row clone and processing using DRAM, we have a lot of videos related to this, and I would refer you to those going forward. But the mindset, I will talk about a little bit. Mindset is that memory is an accelerator. It can do this copy operation very efficiently. So why not put the specialized computation capability inside the memory? We're putting a lot of specialized computation capability to all parts of the system. We have a lot of accelerators, except they're sitting on the left side of the memory bus. They're not sitting on the right side of the memory bus. Why not have something that sits on the right side of the memory bus, as a result has low latency, high bandwidth, low energy access to huge amounts of data without being bottlenecked by the memory bus? And this can be programmed similar to a conventional accelerator as well, as we will discuss. So, okay, you can say that this was not computation, this was copy initialization, and you're right. But we can also support in-memory computation. We can support in-memory and or not and majority functions. Very quickly, you can use the analog computation capability of DRAM. Activating multiple rows performs computation, and you get 30 to 60x performance energy improvements. New memory technologies enable even more opportunities, memristors, resistor RAM, etc., because they can operate on data with minimal movement, and they can also enable other operations like matrix vector multiplication in a crossbar array. That doesn't happen in DRAM because of the operational principles of new memory technology is different from the operational principles of DRAM. Clearly, DRAM is charge-based. New memory technologies are resistor-based, and they're more crossbar-based. But these kind of needs to be examined. Let me talk about DRAM quickly. So if you add the primitive to DRAM, 3-row activation, if you activate 3 rows concurrently, and I'm showing you only 1 bit per row, a row is really 8 kilobytes or so, you get a bitwise majority function due to charge sharing principles. If 2 of these cells are charged, you get the charge state at the end. If 2 of these cells are discharged, you get the discharge state at the end. So this is bitwise majority function using exactly what is provided in a memory chip. Just by adding a primitive called triple row activation, you get a bitwise majority function across 8 kilobytes of data. And if you actually enable it across all of the subarrays in DRAM, you can get across 8 million or 10 million bits in a single DRAM cycle. So clearly you can express this as and and or operation. So you can have bitwise and bitwise or. And we actually have a way of actually implementing bitwise not without adding any inverter, because inverters are already present in the sense amplifiers in DRAM. So now if you actually have bitwise majority and bitwise not, you have a functionally complete system, meaning you can actually implement any algorithm by mapping it into the substrate. Of course, this requires some effort. Some algorithms require less effort, like if you already have database indices that work with bitmap indices, lots of bit level operations. If your database is already designed for this, or web search engine is already designed for this, if you have DNA sequence mapping that's similar to bitwise operations and encryption algorithms that work on bitwise operations, or set operations that work on bitwise operations, you can map your algorithms much more easily to the substrate. And we did exactly that. We mapped the database, Bitweaving database, to our system in simulation, of course, because this is not built. Although existing DRAM chips, again, with limited capability, can support this triple layer activation by violating the timing parameters. And we showed in simulation that you can get more than 4 to 12x performance improvement on important database queries using this substrate. And we have a lot of other results that I don't have time to cover, but if you're interested, you can read this paper for more detail and this book chapter that talks about the bulk bitwise execution engine. More recently, we looked at enabling more sophisticated operations and making this easier for programmability by the user. And I will point you to this work that was published in last ASPLOS. The idea here is user inputs some desired operations, and we automatically, using design automation concepts, create a micro program that can execute these operations efficiently inside the DRAM controller. And we create a new instruction that can be called by the user level program. So basically, we have a user level program that calls an instruction that is executed using a micro program in the memory controller that uses these commands that I have introduced, like the row clone commands and ambit commands. And we show that you can actually get significant speed ups compared to state-of-the-art CPU and GPUs, as well as energy efficiency improvements on complex operations, including convolutions, for example. And if you're interested, the paper has more details. I don't have time to talk about it in more detail. Similarly, you can actually have very interesting security functions. You can implement physical unclonable functions, as well as 2 random number generators inside the DRAM completely by exploiting the circuit level operational properties of DRAM. I don't have time to talk about it, but going forward, security is going to be a lot more important in in-memory processing as well, because one of the reasons why security issues arise is because we're moving data all around. As data moves all around, it gets exposed. If you want to actually keep it in one place, let's say your memory or storage device, and if you actually do security functions on that device, data doesn't move that much. And we really need to have a security infrastructure on the memory side so that we can enable minimal data movement for security purposes. Okay, that was the processing using memory approach relatively quickly. Now let me switch gears and jump into the processing near memory approach, where processor gets closer and closer and closer and closer to memory. At some point, it gets immersed with memory. Here, the interesting thing is to examine some applications. Can we take advantage of this processing near memory approach in some important applications? And we did a lot of applications. I'm going to give you a survey of some of those applications. We start with graph processing. Graph analytics is clearly very important, and it's a very memory bound problem. If you throw cores at the problem, you don't get efficiency. You don't get performance that much, and you clearly don't get a lot of efficiency. Why? Because you get a lot of random memory accesses and little amount of computation in many of these graph processing kernels. So when we start looking at this, we wanted to look at 3-dimensional memory technologies where you have 3D stack memory technologies, where you have logic layer that's tightly connected with memory layers with at low latency and high bandwidth and low energy. You can see that this is hybrid memory cube or high bandwidth memory. And other true monolithic 3-dimensional technologies are under development as well. They will unleash even more opportunities going into the future. And we designed the system for graph processing. So if you look at this, I call this a cube, 3-dimensional cube. Inside the logic layer, you can partition it into vaults. And in each vault, you can have an in-order core. That's what we did. This in-order core can be specialized for graph processing. It could be specialized for machine learning. It could be specialized for other applications like databases. But the idea is these in-order cores can communicate with each other. And you don't move the data. They're programmed with remote function calls, meaning distributed systems programming. Whenever you need to do updates on a data, you send a message to the core that houses the data on top of the stack. As a result, data partitioning becomes important. You partition your data appropriately so that you minimize the data movement as much as possible, of course. And then you program the system like a distributed system using remote function, remote procedure calls, such that data movement gets minimized and you move only the functions, which are actually much easier to move compared to the data. And if you want to scale up the system, of course, you need to have many of these cubes so that you have higher capacity and higher parallelism. And we argued that this actually, as you keep adding capacity, you keep adding bandwidth to the system as well, because you keep adding, you're scaling the capacity together with the processing elements and memory bandwidth. I'm not going to go into a lot of details. It's a full system design. As I said, it's programmed using remote function calls, and we have a lot of prefetching mechanisms to actually enable better bandwidth utilization. And compared to existing systems, this looks very different. Existing systems have the processor-centric, they're processor-centric. They have the dichotomy between processor and memory. As a result, they cannot achieve high amounts of memory bandwidth. But Tesseract system is more distributed, as you can see. Each of these boxes over here is processor and memory at the same time. Processing is near memory, integrated near memory. And you can see that at that time, we had 8 terabytes per second bandwidth available to all of the processors in the system, which is much higher than, more than an order of magnitude higher than the best system that we had at that time. And the performance is commensurate, basically. You get more than 13x performance improvement on 5 graph processing algorithms we examined. Later work actually built on our work, and they basically showed that by optimizing the system, many different data mapping, graph partitioning, scheduling, interrupt scheduling, etc., they basically can get about 2 orders of magnitude, 100x performance improvement on these important applications. Energy reduction is also commensurate. We show that you can get more than 8x energy reduction. Later works actually show that you can actually improve it to almost 2 orders of magnitude. So I find this fascinating. There's more detail clearly in the paper and later papers that built on it. More recently, we've been looking at algorithm architecture co-design for graph mining or more sophisticated graph analytics. And we've been looking at both processing using memory and processing in-memory systems. And we have a set-centric formulation of graph mining problems. And I would encourage you to take a look at it, because if you actually optimize the formulation of the algorithms and map them to the processing using memory as well as processing near memory architectures, you can get a lot higher performance and energy efficiency improvements than what I described before. Now, let me talk about, let's say you don't have the luxury to change the entire system, all of the algorithms, coherence, virtual memory, etc. But you can do limited offloading to memory. What can you do in that case? And this is actually an important issue to talk about, because you would like to have this paradigm adaptable, meaning that you would like to provide some baby steps to industry so that industry can offload simple functions to memory so that you can take advantage of it over time. And over time, maybe you change the entire system step by step. So we did this study together with Google for over the course of 1.5 to 2 years, actually. This is a relatively old study right now, but the results actually are representative today. Clearly, energy consumption is a first-class concern in consumer devices, and we studied these important workloads. And we identified that energy cost of data moments is very high, as I mentioned earlier. We wanted to move computation close to data and look at the benefits of that. The challenge is limited area and energy budget, especially in mobile devices. So what we found out is that in these important applications, a significant fraction of the data moment often comes from very simple functions. And we can implement these simple functions in memory using small embedded low power cores like the Tesseract system I mentioned, or small fixed function accelerators, or reconfigurable hardware. I would argue that we want heterogeneity on the memory system as well. So we really want all of these at the same time, in my opinion, going into the future. And if you actually do this offloading carefully, identify the functions and offload them, you can improve performance energy by more than 2x. Clearly, this is not 10x or 100x, but this is a lot less effort than what we have discussed earlier with building a graph processing engine completely from the ground up, changing the programming model, changing the coherence model, changing the virtual memory model, making it physical memory. So basically, you can get significant performance improvements by functional offloading as well. Just to give you an example, in machine learning inference workloads, a significant fraction of the energy comes from data movement, and a significant fraction of the data movement comes from preparing the data between the layers, for example, packing and unpacking and quantization. And the paper has a lot more detail on all of these workloads. I'd encourage you to take a look at it. So there's a lot of other examples, which I will not go into in much detail. I will mention 2 later on, but GPUs can actually benefit from this paradigm. You can have a main GPU, you can have simpler GPUs in the logic layer, and you can have distributed GPU processing with processing in memory. You can take a look at that. You can make it transparent to the programmer if you're interested. You can accelerate linked data structures, which are very latency critical. You can accelerate dependent cache misses. You can accelerate prefetching mechanisms. You can accelerate climate modeling, which I will talk about in a little bit. You can accelerate approximate string matching near memory. You can accelerate important applications like time series analysis, which is used in many scientific workloads, astronomy, economics, etc. And you can get significant speed ups in your data. More recently, we've been looking at, again with Google, analyzing Google neural networks. These are proprietary neural networks used for edge devices at Google. And we wanted to understand the inference bottlenecks. I'm going to give you a quick overview of this before we end. I'm not going to talk about the executive summary, but we basically study 24 edge neural network models that are actually quite interesting. These are commercial. And we see that there's a huge diversity across the models. There's a significant variation in terms of characteristics of the layers, like parameter footprint and arithmetic intensity. So, for example, LSTMs are completely different from CNNs in this particular case. And the second, even within each model, different layers within each model exhibit significant variation in terms of layer characteristics. For example, the operational intensity is up to 200x different across layers, and flop per byte is actually up to 244x different across layers. The question now becomes, how do you actually tackle this diversity within and across layers? So today, the way accelerators are designed, they're very monolithic, and they're very compute-centric also. Even though they're systolic arrays, they're still compute-centric. Data still gets into the systolic array. Right? So the idea with our approach, Mensa, is to have heterogeneous set of accelerators. One of them is compute-centric. 2 of the other ones are data-centric, meaning they're near memory accelerators. And if you actually design the system such that compute-centric and data-centric accelerators cooperate with each other, and you have a runtime system that can schedule the layers appropriately to based on the characteristics of the layers, whether they're compute-centric or whether data movement is a huge limiter, then you can both optimize the design of the accelerators as well as the design of the system, and you can get significant performance and energy improvements. And we found out that the energy improvements and performance improvements compared to a state-of-the-art Google Edge TPU is more than 3x in this particular case. And we believe that actually performance and energy improvements can be much higher if you start optimizing this heterogeneous acceleration paradigm that couples compute-centric accelerators together with data-centric accelerators. Okay, let me give you one other example. We've been looking at FPGA-based near-memory acceleration of data-intensive applications like weather modeling, climate modeling, as well as genome analysis. And this paper summarizes some of our results. Here, we collaborated with IBM, and we basically looked at a PowerOS 9 CPU, and we have a high bandwidth memory-enabled FPGA board. And essentially, you can accelerate critical parts of weather modeling and genome analysis on an FPGA-based accelerator. I will not go into the details, but we've actually examined 2 communication technologies, memory technologies, and 2 workloads. And we found out that you get very large performance improvements and energy improvements compared to a state-of-the-art IBM Power 9 system at the time we did these experiments by just offloading critical functions and implementing them in an FPGA that is basically tightly coupled with high bandwidth memory. And you can see the numbers in this paper, and if you're interested, you can read the paper as well. So I think these numbers are actually quite interesting. These are evidence showing that maybe if you revisit the entire stack, we can unleash significant benefits doing memory-centric computing. But we do need to revisit the entire stack. I believe we can get there step by step with simple ideas, simple changes to the system. And this paper talks about the simple changes to the system as well. And this is another paper where we talk about workload and programming ease issues. That brings me to how to enable adoption of processing in memory, because clearly whenever you have a fundamentally different paradigm of computation, adoption will become an issue. You may design the greatest hardware, but if you cannot think about the adoption issues, and if you don't solve the adoption issues, this may never be enabled. So there are many barriers to adoption in a paradigm like this. Applications and software are at the top, and they're perhaps the most important. Ease of programming. How do you design the interface and compile and hardware support? System and security support. And there are many issues over here: coherence, synchronization, virtual memory isolation, communication interfaces, runtime and compilation systems, and infrastructures to assess benefits and feasibility. I believe clearly these are issues, and people are working on solving them, but all can be solved with a change of mindset. Today's mindset is very processor-centric. We need to get rid of that mindset and think about data-centric. If you have a data-centric system, how would we design the system? We cannot say, okay, processor-centric system is this way. So how do we actually, we cannot basically take processor-centric principles as a given. For example, data mapping is done in a particular way today in a processor-centric system, but maybe data mapping should be done a completely different way in a data-centric system. So this means that we need to revisit the entire stack, but we can do it step by step. So there are many questions over here. I'm not going to go into the details of any of these works, actually. How do you keep it simple? That's important for adoption. How do you maintain coherence between the processor and memory? That's important for adoption. And there are multiple works that I flashed you over here. And traditional coherence models don't work very well. Coarse-grained coherence doesn't work very well. Fine-grained coherence is a little bit better, but it causes a lot of communication between the memory and the CPU. So if you really want to partition an application between a memory and the CPU, you will need to think about new coherence mechanisms. And we have some coherence mechanisms that we have proposed in these papers that you can take a look at. How do you support synchronization? This is an important issue, especially if you want to scale the applications to many, many applications. And how do you support virtual memory? Again, another important issue. And there are other adoption barriers that I'm not going to talk about. But today, the good news is people actually started to solve these adoption barriers. Processing in memory in the real world is happening. This is UpMem, a company that we actually work with. It's a startup in France. They put engines that inside the DRAM chips near the DRAM banks. These are multi-threaded engines that you can program using very similar programming models to today. And these are real, as you can see. We experiment with these systems. And we actually have a lot of talks and papers that talk about our findings in the system. You can see that's a multi-threaded system with a pipeline that's similar to today's systems, with caches and scratch pads that are similar to today's systems, but they're very near memory. So the data movement doesn't go beyond the bank unless you need to communicate between these processors, of course, and you get low latency access to the data in this bank. And if you're interested in the details of this system, its summary and benchmarking, you can find a lot of information in our papers, and we release the benchmarks so anyone can actually experiment with them. They can get in touch with the UpMem company. They can actually do the experiments if they're interested. and they can make use of the material that we put out if that is appropriate. I talked about FPGA-based near memory systems already happening. I've given you some real results. And to actually take advantage of these systems, we really need to have methodologies that can aid the programmers to answer the question, what should be offloaded to memory? I have this function, I have this algorithm. What part of it should be offloaded to memory? What part of it should stay in the CPU, for example, or the GPU? And for this, we really need to have methodologies. And we've developed this methodology based on rigorous profiling of applications. We analyzed more than 300 applications on important domains, as you can see over here. And we developed a memory bottleneck analysis methodology, which classifies different functions in these applications into 6 different memory bottleneck classes, as you can see over here. One of which is compute bound. The rest is different kinds of memory bound. And based on this, you can decide what to offload to memory. And the paper has a lot more detail on how to decide what to offload. And this is also all open source, as you can see. And you can find more information about the paper as well as the benchmarks. More recently, Samsung has announced that they actually are putting function in memory, specifically multiply and accumulate operations inside the memory so that they can activate neural networks. This is a good sign. Actually, even more recently, SK Hynix also announced this, something very similar to Samsung. This was announced, I think, a week ago, or maybe it will be announced in the ISSCC in the coming week. Sorry about that. I don't have a paper related to that. But basically, these accelerators are accelerating neural networks, and big companies like Samsung and Hynix are actually trying to get these into the market, as you can see. And they are limited. They're of limited capability, clearly, but they can reduce the data moment bottleneck. And going forward, this is the first generation. So our experiments with in-memory processing systems also show that these are first generation systems. They're competing with processor-centric systems that have been designed for 70 years or more than 70 years, right? So put this in the perspective of history. If we actually optimize these data-centric systems or memory-centric systems enough times, maybe they will significantly outperform, even more significantly outperform existing systems that have been optimized for decades and decades in terms of both manufacturing, programming, architecture, and all levels of the stack. Okay, so Samsung has some other prototypes that I'm not going to talk about, but I will end with this. Basically, I will say that future processing in memory systems can enable actually new medical and health platforms, and genome sequencing and analysis are part of it. So if you're interested in more lectures on this, we actually have a lot of material online. I will mention this tutorial that we delivered that's much longer, that talks about a lot of interesting issues in processing in memory. And you can find a lot of other tutorials online as well. So a big challenge and opportunity for future for us is, how do we enable fundamentally energy efficient systems? That is data centric, in my opinion. How do you enable fundamentally high performance systems? They have to be data centric again, in my opinion. If you actually change this fundamentally reliable and secure, I would also argue that they should be data centric. And one thing that we really need to take into account in our systems is, how do we minimize the data moment? So we're not going to talk about the data driven and data aware computing architectures, as I expressed in the beginning, but you can find more information in a tutorial that I gave in the International Electron Devices meeting. And there is more information that you can find in our courses as well, which I will link to at the end. So let me conclude. I believe it's time to design principled system architectures to solve the data problem that we have, which reflects itself as a memory storage communication problem. We need to design complete systems to be truly balanced, high performance, and energy efficient, which will lead us to intelligent systems, hopefully. And I believe they need to have a blueprint of data-centric, data-driven, and data-aware systems. We want to enable data computation capability inside and close to memory. And hopefully I've convinced you that this can lead to orders of magnitude improvements in both real systems as well as simulated systems. And again, these are the first generations. What about the second, third, and fourth and fifth generations? They will be hopefully a lot better. This can enable new applications and computing platforms, and hopefully enable a better understanding of nature as well, and who knows what else. And this is my blueprint for fundamentally better architectures. And nature, in my opinion, is similar to this blueprint. Today's architectures are very processor-centric, and I don't believe that that's the only principle that's employed in nature to actually design a distributed system that looks like this. In fact, we know based on evidence that this system is very much memory-centric and communication-centric, as opposed to centralized. But of course, to enable this, we need to revisit the entire stack, and we can get there step by step. And these are some principles that I actually mentioned in this talk, but I didn't pinpoint them in a single slide. Here you can find them in a single slide. More important than anything else, we need open minds to actually think data-centric. And this is a shorter paper that we have written that talks about this blueprint. So with that, I will acknowledge people who have funded our research. Thank you very much. Without them, this research would not have been enabled. And we've been doing this research for multiple decades right now. And more importantly, I will acknowledge my group whose work I have been presenting in this talk. And you can see some of the faces in the group over here. And we release newsletters. This is the most recent newsletters that we have released that you can find online. I will also say that reference papers, talks, and artifacts are all available online on our web pages, YouTube channel, and GitHub webpage, which I believe is important. We actually believe in open sourcing everything as much as we can. And if you're interested, you can actually join our courses. We live stream them, and anybody in the world is welcome to join our courses. And we have a processing in memory course. A new incarnation will start next week. And also our undergraduate course will start next week as well. And you can find it online here as well. Well, thank you very much. I hope I'm on time. I'd be happy to take any questions that may have come about.
Thank you so much, Dr. Murthy. This is, I think there was, we almost had to, we have to sort of shift our frame or references of thinking. As you said, I think we've been so tuned to designing systems in a particular way. And actually, as, even in the industry, we can see as we are building more and more systems that are quite, as we continue to collect more and more data, the challenge continues to be about how to sort of efficiently process that. And this, the pointers that you've given, it's also good to know that the direction in which research is going on in among the manufacturers of memory in this space is taking us in a way that's going to lead to systems that can at least be more energy efficient. As you mentioned, it's 67% energy spent only in data movement is in a world where we are so conscious about climate change and its impact and the growing importance of systems. Yeah, thank you. That was really, really engaging.
Thank you.
I think there are a number of things around the slides, and I think you'd shared tons and tons of research papers, which will be made available, I think, after that talk. I'm sure you can give the references to those.
Yes, I'm happy to share the slides.
There were a couple of questions in the Q&A. Maybe just take one or two of them. One question was around, doesn't the CUDA language already send instructions directly to the GPU? And it's sort of like similar idea around the fact that it's avoiding latency of transferring information. So
yeah, certainly. I mean, but that's very much specialized to a GPU, and a GPU is another processor-centric system, I would argue. So we have mechanisms today to actually send instructions to our accelerators or offload computation to our accelerators. They're usually very good at coarse grain offloading, but they don't take into account memory clearly. Today, memory is not considered as an accelerator. Going forward, if we make memory as an accelerator, we need to think about what should be the programming model. Potentially, if you're NVIDIA, of course, you would probably argue that CUDA should be modified to take advantage of in-memory processing, and that makes sense, of course. But basically, our programming frameworks need to be modified so that we can communicate with memory in a much more intelligent manner.
Thank you. I think there was another question around like when you talk about co-locate memory and CPU storage, how does that compare to the connection machine experience?
Oh, okay. So old times, let's say. Yeah, I mean, certainly there were a lot of good ideas in the old times for parallel processing. I think connection machine is a machine that's ahead of its time. It certainly looked at more tightly coupling processing and memory, but that was not its main focus, let's say. Its main focus was really parallelization at large scale, especially bit serial parallelization, for example, was very successful for some workloads. So I would argue that there are some similarity in the approaches, but we need to be a lot more aggressive in integrating memory and computation together today. I believe connection machine gets memory and computation closer, but we need to be much more closer today, like the UpMem machine is doing, for example, or Samsung and Hynix are doing. They're putting computation units inside the memory bank. And that has not been done, as far as I know, in any commercial machine in the past.
Great. Cool. Thank you again. Thank you for sharing your your brilliant insights in this. I think it ties in really well with just having to look at this problem from multiple different perspectives about not just speeding up the the processor, but also looking at the overall architecture of how we are designing systems nowadays. There's maybe one final question if you have time.
Sure. I have time.
Yeah, so it was, the question is, how can Moore's law affect the memory-centric or data-centric architecture?
Okay, that's another great question. So there are two kinds of things to think about here. Moore's law certainly has been exploited very well in processor-centric architecture, and we're kind of approaching its limits at this point. We need to think a bit differently to exploit it in the processor-centric domain. I would argue that memory-centric computation is overcoming some of the limitations of what we've gained with Moore's law. With Moore's law, we've gotten very fast logic, but interconnect has become a bottleneck. And one of the reasons we're having this bottleneck today is our logic has improved greatly, whereas our interconnect did not improve greatly due to scaling and Moore's law as well. So I would argue that memory-centric computation can overcome some of the issues that were exacerbated by Moore's law. But clearly, once we, let's say, transition into a more memory-centric system, what is our limitation going to be? Are we going to be able to really scale the transistors inside those devices? I don't think we're there yet. We have not really explored how efficient we can make transistors in a memory process, for example, or combined together with a memory process. So from that perspective, I think we will have some time to exploit until we reach some scaling limits. And we have a lot of area to actually put transistors inside the logic layer as we think that way, as we think more data centric. And if you actually think about even further into the future, some of these emerging memory technologies are much more scalable because they're much more resistive. For example, they can actually enable better scaling than existing memory technologies. And if you think that way, then our scalability can be unleashed even better, and they can enable in situ computation, which is what I call processing using memory. And I believe we need to think toward that direction also, so that we don't have the traditional limitations of existing processors by doing near memory computing. I hope that was clear.
Yeah, I think definitely. I think the way you described it, at least earlier on, is we are, processors or the design of processors had the benefit of being optimized over 7 decades. And given that we are sort of starting on this journey, I'm sure there's a lot of areas that we can that we'll look to sort of explore and then also optimize. So thank you very much. I think we are at time there now. So thank you again for taking time. So